Okay, so what we just finished showing was that the for velocity as defined here um, does give you the correct velocity transformation uh, when going from one frame to another, and that is cool. In fact, it's a very elegant way of actually deriving the velocity transformation, but you have to know already about four vectors, and you have to know one of the key properties of four vectors is that their components transform according to the Lorentz transformations when you go from one coordinate system to another. Okay. Now, since the since the four vector, since we've already discussed the fact that a four vector dotted to itself is an invariant, right? So we showed that with the four displacement, what we would call just the four vector, the four displacement vector. But that's a property of all four vectors, is that the dot product of a four vector with itself gives you something invariant. So what's the value of the invariant associated with the four velocity? That is, what is its magnitude? Okay, so the easiest and maybe most elegant way to calculate this, to compute this, is to transform from a general coordinate system, a general reference frame where the particle is moving with some velocity u, into a coordinate system, into a reference frame where the particle is at rest. In other words, find the rest frame of the particle. And in this case, ux is equal to uy is equal to uz equals 0, obviously, and also gamma is equal to, which we define to be 1 square root of 1 minus u squared over c squared in this case, and this is going to be equal to 1, okay, because u again will be equal to 0. Okay, so in that coordinate system, right, the four velocity is just equal to c 0 0 0, and so u prime dot u prime, which by the way has to be right the same as any general four velocity dotted into itself, is just equal to c squared. And so what we see is that the magnitude, okay, of the four velocity is equal to c. So that's interesting. That may be puzzling because some particle, you could imagine that in general some particles can move more quickly, some more slowly, but for all particles, no matter what their velocity, the magnitude of their four vector of their four velocity is equal to c. Okay, and but actually this might seem a little bit strange, but it's not really strange, because again we need the magnitude of a four vector. We need that to be scalar. We need it to be invariant, and the magnitude of a scalar, right, as I said, has to be invariant. So if you change reference frames, some particles that were going fast will now go slow, and some which were going slow may now go fast. And so the spatial part of the speeds, or the magnitudes of the three velocities, are relative, but the magnitude of the four velocity basically has to be an invariant. Okay, so that basically ends this lecture on scalars, four vectors, and the four velocity. The next lecture will deal with the four momentum, which is how we started this lecture. We wanted to find a generalized momentum that would be conserved. So we're going to find that momentum in the next one, and it's a four momentum. And then we'll see what that means in terms of conservation of momentum and conservation of energy.